Right, so starting from where we are left out from yesterday, so I already went through BST, insert, and remove, but I mean, it was last night, but I still do want to review it one more time because I had a little confusion about the remove part. It was a lot of code. I wouldn't say that, but just like a lot of recursion stuff, which my body or my mind didn't quite get it yet. So I think I'm going to watch the video of Neat Code one more time about the insert and remove for BST, and perhaps we can do a problem after that. So let's see. It's quite some time. I But unfortunately for this part, I do have to black out of the black out my screen for the copyright thing, for the copyright issue. So just I'm gonna just do that. All right, let me get started. All right, so I just finished about the BST insert and remove. Basically, I think I figured it out. I think I did understand. So insert part was pretty easy. If we're gonna check out the code, let's see. Let's take a look at it. Let me just review it real quick about what I learned. So, all right. So, I mean, this is okay. This is tree node, right? So for inserting, it's pretty easy. Let me just draw it out. I think y'all can see this, right? I don't know. I don't think it's really clear. I couldn't figure out a better setup with my current equipments and stuff. But let's see. So removing a node, let's take an example of the node that he gave us from the, from his thing, which is, let's you know what, I might just look it up on, so let's say this node right here, right? So 4, right, and 3, 6, 7, 5, and 2. So I don't know if you can see it, but that's basically it. It's like this. This is horrible. You know what? I do like to draw on a paper with a pencil, but I do have this equipment too, so I can show you what I'm talking about. Alright, so what I can do is, draw it on this. Bro, I'm glad I got this Vacom's tablet. It's actually good for, good for setting things up. Let me pull this out. Ooh. No, what should I open? What should I open? Right, so Oop, great. The backcom is not working for some reason. Let me try this out. Let's see if it works now. Okay, it's not working. Our backcom is not working either. So I think the only way to fix it is, it happens sometimes, there's a bug. In order to fix it, I need to connect the device. So it's not connected right now. Usually it gets fixed when I restart my computer. But that'll end the stream, so I don't want to do it. You know what? Alright, we're not going to be using it, unfortunately. Let's just use the paper. I'll make sure I got it next time. So, I know you won't be seeing anything, but let me do it for the purpose of teaching myself. So here's our tree. So inserting is basically, there is, okay, so inserting. Let's say we want to insert give me a second actually. Insert, how did that work? So for inserting, okay, so it was like this. Inserting worked like this. So inserting is, so let's say we wanted to insert 7, right? So we have, this is the complete node example that we have. Let's say we wanted to insert 7, which we already, let's say we already have these nodes. No, and then we have 5 here. Here we don't have anything here, and we don't have anything here, we don't have anything here. We wanted to insert the node 7. I mean, we start from 4. So we check the value. Is 7 greater than 4? Yes, it is. Then if that's the case, we go on to the next, the right subtree of it. Okay, let's say what if this was an empty tree, right? It didn't have any value. Then what we do is we just return the tree node with a value 7. That's it. Or else, it's bigger, then we go to right. And since we're doing it recursively, we set the root dot right equal to okay, I don't know how to explain this. So we're putting a root.right equal to the right side of the, so that means if it's bigger, then if it's bigger, we come to the right subtree of it. Is 7 bigger or less than 7? Since it's bigger, we go to the right subtree of 6, node 6 again. All right. After we're going into that, so we finally come to null, which we don't have anything here. When it's equal to null, we just create the node. So basically it's like tree node dot 7, right? That's what we do, and we make it equal to the root dot right. I mean, this part is going to be done recursively. I mean, at first I was pretty confused about it too, but later, since he showed the code, it was much more clear. Yeah, so that's basically what we do. After creating it, we just connect it back to the root, and this new subtree, and we connect it back to the original root. So this is done. Okay, so for remove, all right, this is done for insert. All right, I know it's not a good explanation, but you get the idea. I get the idea, most importantly. For remove, so remove has two cases, which is case 1. It only has 0 or 1 child. Okay, and case 2 is it has 2 children. So for these 2 different cases, we handle it differently. It's very different. So let's say this is our big node. I'm trying to think if I have a better, this would have been really good, but it's not like that. So what if I just try to put it right here? Okay, all right, you can't see this either, never mind. Let's just stick to what we have already. Okay, all right, so remove, right? So we have case 1, which is the node has 0 or 1 child. Case 2, the node that we're removing has 2 children. So in order to do this, first of all, we have to know how to find the minimum value of a tree, right? So that is very easy. So it's basically like searching in a binary tree, which the time complexity would be log n, but also worst case scenario, so log n basically also means the height of the tree, which we can just say h. So this is the height, right? Let's say this is the height, this is h. So the time complexity we can either refer it as O of log n or just O of h, which is the height of the tree. So, okay, let's talk about the removing part. Let's say we wanted to remove 2. In order to do that, of course, we have to traverse through the tree first. So we see if node 2 is smaller than the 4. Yeah, it is. We go on to the left subtree. Is it smaller or bigger than the 3? It's smaller, then we go to the left. And we come to the node, we found it, right? We found it. So what we do here is, since this is the case where there's only, that's okay, so we check what is the left subtree of the 2 or the right. So they're both null, so that means it has 0 children. It has 0 child, so that's case 1 where it has 0 child. Then if that's the case, we just put this, we just make this equal to you know, this no right here, we just make this whole thing equal to null, which we can do it as equal to you know, the right subtree of the node 2, which is null. So this whole thing would equal to null, and we make it equal to the node dot left, and it'll be node dot left. So so on and so on. I think that's how it works. Just let me make sure if that's correct. If it's smaller than, yeah, basically the code looks like this, right? So if the value is smaller than the root value, then we basically go, you know, left side of the subtree, which we make get equal to root dot left is going to equal to, you know, remove. We call the function again, so recursively, that'll be remove root dot left, right? Because it's left subtree, and the value. We make the root dot left the pointer equal to, so that's why that's recursively, right? I'm already confused about like how recursion works, so I'm not good at explaining this, but as the time moves on, you know, it'll click in eventually, like my friend told me. But so I don't think I'm at a stage where I can teach you how this would work, but I'm just trying to explain it to myself. That's actually the whole purpose of the stream, to keep myself checked in. So we do that, and then okay, so let's just run this code. Okay, we go into the parent node, it's 4, but we want to do 2, so it's not a null. If it's not null, then we check, okay, it's smaller than root dot left equal to remove dot root dot left dot value, which we come to 3, and 3 gets you know, gets so the left subtree, we run the function again. We check right here, okay, is the value, you know, it's smaller or bigger than the left or right, whatever, and it's smaller, we go to the left side right here. Okay, at this here, okay, is it the same? Is root dot value bigger? No. Is it smaller? No. So that means it's the same. So we run the last part of the code of it. So if is this null, we check if the left side of the node of 2 is it null or not. Okay, if it's null, then we just return the right side of it. Okay, so since this part is null, right, give me a second. Since this part is empty, so we just return this. If this is not empty, if this is not empty, this is not empty, but this is empty. Yeah, so in that case we'll just be returning this, and we're setting this equal to the root dot left. So the entire this part will be eliminated, right? It'll be gone, and it'll be equal to null instead. So the node 3 dot left will equal to null. So that basically means that we removed it, and then the new subtree, this part will be equal to this thing, the parent, no, I mean the root, the original, the parent root dot left will be equal to this new subtree. Right, that's basically it. Okay, what if we remove the, if there's another case, okay? So we did the case where, okay, we did the 0 child case, now do the 1 child case, which is still case 1. Very easy, right? We traverse through it. So let's do 3 instead this time. Let's do 3. So 3, is it smaller than the root? Root is 4, right? Is it smaller or bigger? So it's smaller, we go on to the left side of the subtree, left side of the root, so which is the left subtree. We go in there, so we're looking for 3, so 3 it is. So since we're trying to remove it, we check if the left 3 dot left is null or not. It's not null. If it's not null, then we're connecting this. All right, no, wait. Give me a second. I'm confused one more time. I think it's normal, but let's see. If it's same as not with the letters. Says, is it null? Is the left side null? No, it's not, right? Then we check if the right side is null. If it is equal to null, then we just return the left side. Right, all right. So okay, so basically, yeah, this will be equal to this. Yeah. All right, I mean, I figured it out. Yes, that's good. All right, so I know I didn't explain anything, but basically, so we check root 3. Is left side of it null? It's not, right? We check the right side of it. Is it null? Yes, it is. Then if that's the case, then since this is null, we just return the right subtree. We make it equal to the, the root dot left, which directly, we just eliminate this part. It'll be equal to this. Okay, yeah. And then, all right, the last one, case 2. For case 2, all right, so let's say case 2. Let's remove the parent node, right? No, not the parent node. Let's remove the root, which is 4 itself in this case. In order to do that, we have to set node 4 equal to the smallest value in the right subtree, which is going to be 5. That's the only case where this stands. If you want me to explain this, that's going to take a very long time, so we won't be doing that, but I do understand. So what's important is that I understand it, okay? I'll care about you more later on in the videos, I'll try to make a better content if this channel actually grows and stuff, but I know for now nobody's watching. It's just for my own documentary. All right, if that's the case, we go back. All right, so that's we just find the minimum value of the right subtree, and we make it equal to, we make that equal to the original root, which is 5, and then we eliminate the 5 that we found here, so that's going to be gone. That's the case, yes. Okay. So. So since that's the case, I think we can we can perhaps look into a video. Sorry for waiting. Just give me a second. Just give me a second. Alright, let's do this problem. Insert into a binary search tree. Since we're not going to need this, let me just delete that. Don't save. Let's set a timer. This is a medium question. I do want to put like 45, but let's do 30. Insert into a binary search tree. You are given a root node of a binary search tree, BST, and the value to insert into tree return root node of the BST after the insertion. It is guaranteed that the new value does not exist in the original BST. Oh, so he's talking about like there's no duplicate case. Notice that there may exist multiple valid ways for insertion. As long as the tree remains BST after insertion, you can return any of them. So we gotta... So basically saying that you have to remain the balance, right? You know, I'm hoping that So Ha 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 ha. So this is one way to do it, which I think this is the way that I prefer. Another way, if alright, so 5 literally inserted here because it's, you know, this is still valid. I see. But doesn't the balance of this will be break? One, two, 1, 2, 0. I guess it's okay. That's still a BST, I guess. Root 40, 30. Alright, I don't think I need to read all that, but let's get started. So, I don't think I need this. Let me just try it out in case. So, first of all, what we do is if we gotta check if the originally, if the root has any value in it, right? Does it have any value in it? If not root, then return non. That's one thing. That's out of the way. No. If it's not root, then we have to make the treat node dot value. We have to insert it. We have to create. That's not removing. I forgot. Okay. We're gonna check here. If So base case is if it's not a root, then we create it, right? So second of all, we have to check now. Is the value smaller or bigger than the root? So let's go from the small case, which is left, right? So if value is smaller than the root dot value, right? If it's smaller, then we have to do root dot left. That means we have to go to the left side of it, left side of the tree, left subtree. I can't type. I can type. And we make that equal to, that'll be insert into BST. This is going to be root dot left dot value. All right, we're gonna check if we can check the left subtree to where we can insert it. Else, if value is bigger than the root dot value, which is we're going to the right subtree of it, then that's the case. We just do root dot right equal to insert into BST and root dot right and the value. Okay. Then the last case is where we can just return the node, not return the root. I think it is as simple as this, hopefully. Insert into BST. Yeah. Why would this happen? I don't know what I messed up. Give me a second. I gotta check this. I don't know. I don't think I did anything incorrect. I mean, obviously I did, but what is it exactly? I honestly do not know what I did wrong here. Why wouldn't it work? What do you mean it's not defined? Insert into BST. It is correct. Time is running out. What is happening? Let me see. Oh my god, I figured it out. I know what the problem is now. I keep missing this part about the Python, which, you know, I forgot that there's self. So now it should work. No. I meant by bro. Okay, since it's a self, I don't know. I don't know how to say it, but you get it. This is time complexity. Is this random? I think this is the best time complexity, right? Okay, I think it is, yes. I mean, this question was basically what NeetCode taught us in his video. Like, he talked about inserting and remove. That's why I got it so fast, but even though still it would not be a too hard of a question. But there's a mosquito in my house. Wait, I gotta kill it. Oops, my bad. I didn't catch him. But yes. So that's inserting. I mean, I know that there's another question. So let me just, do this one more time. Sorry about that. Inserting. Let me see what the other question is. So this is done. Yeah, so because I had to go into NeetCode's page. That's why I had to blur it. So the second question is deleting a node in BST. How about we do this? I have to go eat. Let me come back after eating. Let me close the stream for now. After I'm back, we can work on this problem. This is also what he taught. I guess these are like really good questions to just see if you understand the concept of like deleting and inserting. I think I did. So let's call it